detectors
So,
to
sorry.
lie, sure, to lie detectors that are used by the FBI and the National Security Agency to measure how whether people are telling the truth or not when they're being interrogated, and very a lot of some equipment that's used for measuring detecting whether a landfill lining is leak proof or not, so that you can make sure that your landfills are not leaking. And so what I was previously, before we started Martin Company, I was with Analog Devices and got to see electronics, from a semiconductor company standpoint. And so for 43 years, we've been designing electronic equipment that makes measurements. And just like Tommy, we do hardware and firmware and software design. Most of the interesting thing about our industry is the intelligence has kind of moved from being in the analog electronics front end to now it's all in digital form, like in a processor, microcontroller. So we're doing the same kind of measurements we've done all these years, but now we're doing it with a lot more digital processing. And I think Tommy and I may be a lot alike in this. I love electronics. Electronics to me is the most I mean, I can't see myself doing anything else. I really enjoy designing and manufacturing electronic circuitry and figuring out how to make it work correctly, and especially electronic circuitry that's making some kind of weird measurement that's not easy to make. That's kind of it. I give you some statistics on our company. 43 years in business, 3,700 projects, about 300 customers, and right now we have about 17 people, and we have 6 software engineers, 3 hardware engineers, a mechanical engineer, and then our manufacturing and front office folks.
That's good. All right. Let's see.
So
Questions or comments?
I think I have a quick one. So you mentioned you've seen a lot of shift from analog electronics to digital electronics. Are there any, well, given that, are there any skills you guys are looking for in your employees, or any skills you think students who are interested in working in electronics should develop beyond, say, that which they learn in the class, like beyond your digital electronics class, beyond your circuitry class?
Well, yeah, and when I said that, I should clarify. It's not that analog electronics went away. There's still a ton of analog electronics to be done, but now you've just got a lot more electronics in general. So a higher percentage of it now is digital. I just advertised for an engineer here recently. In fact, I told some of the guys with there at U of H, and basically I was looking for a bachelor's degree, and if I could find one, a master's degree in electrical engineering, and somebody that could draw schematics, lay out PC boards, both analog and digital, and also somebody that could fix stuff. Because every time you do a design, something doesn't work on it, so you have to fix it. First thing you have to do is debug it or troubleshoot it or diagnose your design mistakes. And so that was a hard position to fill. I could not find, it was very difficult to find somebody, and I did find somebody, but it was very difficult to find somebody that had both analog and digital and could draw schematics and lay out PC boards.
So we're about to hire someone, and actually they're trying to hire my replacement. So are people that eventually replace some of the skills I have, but yeah, we're looking for actually someone with very similar skills to what he just detailed. We have a number of people that can do the software, firmware, and do that part of it, but doing hardware design and doing the especially the analog design and understanding that the front ends is, I think that's tough to find. You know, I think John and I have been around so long that it's almost second nature to me to do this stuff. I just look at things and kind of drill down very quickly to the important parts because I'm so accustomed to looking at it. Those are skills, and quite frankly, when we connect up a new PC board and apply power to it first, the reason why we call it a smoke test. And there's a certain part of the time that it either takes out the fuses, or we always start with the power supply where we limit the current, because you know, when you first turn it on, you know, a good part of the time there's something going wrong, and
Sure.
you have to troubleshoot it down. I try not to do the finger test where you go find the hot spot with your finger. I use an infrared gun or a temperature device to see if I can find it. And I usually kind of slowly turn up the current till I get a hot spot, and then I go find it. But there's just not that many people that have the skill to really track things down and fix things and figure out what's wrong quickly. And when you're designing, you know, the boards we have, almost all of them have 3 and 4, 5, 6, 7, 8 regulators on them. Some of them are boost, some of them are buck, you know, boosting current, boosting voltage. Some of them are doing just regulation and low noise, and you got to know how to do all that. And then with microprocessor, then all the digital circuitry that we're doing things with. So it's such a combination, and that's part of what makes it fun, is you get to do all that. So I did my first microcontroller project in probably 1976. It was I think it was a Motorola 6800. You remember that, John?
Yep. Yep. Absolutely.
Yeah, and we didn't have any development tools. We had to design our own little programmers and everything. I did it while I was over at the medical school, but I hand wired all that stuff. I couldn't do board layouts, so that was a long time ago.
Yeah. The other thing that Tommy just mentioned that I think is important, when you talk about analog electronics, it's really all through your circuitry. Like he was talking about, all the power supply circuitry, that's all analog. And then if you're connecting to the internet with Wi-Fi or Bluetooth, or you know, any communication standard, that's going to be some analog or RF type circuitry. And then if you're running off of batteries, then you got to figure out how to make all your electronics work at really low power. And that becomes an analog problem. Even the digital stuff then becomes analog, because you're trying to go in and make a microcontroller, like Tommy's talking about, draw the least amount of power possible. And so, and then everything you're usually trying to measure something or display something to a user, and so that kind of could end up becoming an analog problem. So to me, electronics is just electronics. It's all, whether it's analog or digital or RF or whatever, it's all, you know, it's kind of all electronics.
Right.
So if you have sort of a passion for it, that's in your favor. If you're afraid of all that and you want to stay over into the software and that, then okay, but you're missing half the fun. There's another aspect that we would look for, and that is it's sort of problem solving skills that used all those other courses you took, all that physics and all those things you took, and then you took a course from, we had to anyway, a course from each of the other departments, mechanical engineering, the industrial engineering, all those different courses. I've used every single bit of that.
Yeah, me too.
Really?
I mean, how many of you thought you would think you'd have to calculate how hematocrit of blood and how you're dealing with that in a certain circuits where you're trying to figure out how you're measuring impedances of things and stuff. And what temperature does to that. So you have to be able to think clearly through all of those things. So, designing pump systems. I've designed dialysis machines. And so you have to understand pumps, you have to understand flow, you have to understand pressure, and do all of those things and integrate that into one project. And that's part of the fun. That's why we get to work on very complex and interesting projects, because we have skills that spread across that. And also how to work with other people. Where we really need strong mechanical design, we work with a partner with a group that's all they do is mechanical design. So yeah, so if you like, you have to know where your limitations are too.
Right. That's
I would say the other thing, I'm sorry, I didn't mean to interrupt you.
Oh, no, I was just going to comment that it's interesting to me that when you guys were in college, you guys took courses from other departments within the College of Engineering, because nowadays we don't do that. The closest,
No, you don't take like thermodynamics or
No,
heat
no.
transfer.
Mechanics of solids.
nope.
You have to take one, you have to take one special elective
I
for
mean,
one
you-
of the
you-
other engineering.
You have the option,
disciplines.
yeah, you have the option of taking,
Right.
say, one of the mechanical engineering classes, or as one of your technical electives, but you by no means have to take it. You could go your entire degree only taking the bare minimum math and science courses, and then fill everything else up with just ECE courses.
Wow.
So
Well, I tell you what Tommy's talking about with the smoke test, when you start dealing with large computers, one of the biggest problems you're gonna have is heat transfer. How
Mhm.
do you get the heat out? And that's where you learn that in the heat transport class. The other thing I was gonna say, when I interview people, I usually ask two questions. I say, how much have you worked on your own car? And of course, that's kind of an obsolete question, because now everybody's got cars that are really hard to work on. But somebody that has worked on their own car is, a lot of times, I know, will be able to, they're not afraid to get their hands dirty, and they can figure out, they can solve problems that are real world problems, like, why is my car overheating or whatever. And to me, that kind of ability to think is really important for an engineer. The other thing that I always look for is always ask people, well, how do you like working with people? I mean, do you enjoy people or not? And if somebody, I mean, that's important to us. Now, you can work for a lot of large companies, and neither one of those may be as important. But for us, we want somebody that could, that can talk to customers, or talk to fellow engineers, or talk to vendors, and be able to not be afraid of dealing with people.
got it. So basically, you guys are looking.
Unfortunately, go ahead.
I was just gonna say, so it seems like you guys are looking for people who are maybe less specialized and have a more breadth, or their breadth of knowledge is greater, so that they can apply to multiple different things. Since you guys,
That's a very good observation. I agree completely.
So one of the other things that happened to me is I spent all those years learning how to solve problems and do math and do that type of analysis. So when you work in the medical device development area, you have piles of documentation. Right now, because I can't dump it off on one of my other engineers, I'm having to write software verification protocols. And it's page after page after page of just writing these protocols to make sure you validate every single specification that's written down. It's very tedious, and it's pages and pages. And so I had to go from, I had to develop the skill set of being able to write and write clearly and legibly, and it took a while. I mean, sitting on my desk these are all specifications and things. They're just my stuff is just full of that, because you have to be able to document everything you do. So your writing skills also, if you're going to work in the medical device industry and you're going to be at a position as an engineer, you're going to be writing specifications. and you're going to be writing all sorts of reports, and it requires writing skills. Unfortunately, it's if you don't have it, you'll have to develop it. I know I did.
Yeah, I think
The other thing I would say on that is I can tell by the way somebody writes how they think. And so when you look at somebody's writing, you can tell, do they think clearly? Can they think in great depth or in great detail? And so you really what I think of is I'm sort of the same as Tommy. I mean, I took English and all that during college. I mean, during my school there at U of H, but I have really grown to enjoy writing because it's one way I have of thinking about something. If I write something down, I can look at it and think about it, so it's a sort of part of the problem solving process for me is to write things down.
Well, it turns out that when you're our age, you have to write things down anyway, because if I don't have a list, if it's not on my list, it won't get done.
we might forget it, mightn't we, Tommy?
So I will tell you that the other thing that I just as an aside, and this is it's a little creepy in a way. So how does the person, like I'm actually kind of an overpaid hourly employee is the way as it turns out, because I charge by the hour.
Mm-hmm.
So I have to document every day. I have to document what I've done that day and charge hours to it. So I keep a day timer. That's what it looks like. That's a day's worth of documentation of work.
Okay.
So I have to do that at the end of the day. Every day I have to do this. So I have to write down what I did and the hours I'm charging to that company.
So you're almost similar to a lawyer building their hours in that regard.
I'm not that bad. I wish I charged as much as they did, but no, I don't get to charge that much.
Shame.
I'm the same way. I charge my time out too. I put mine into a software program that was actually written for lawyers and accountants. And the interesting thing about what Tommy's talking about is a lot of times if you hire somebody from a big company and you tell them to start writing their time down every day, it's really a struggle. People have trouble if they haven't been documenting their time every day, figuring out what they're doing. I mean, what did they write down, for 8 hours of work? What did I get done today?
Yeah, I mean, I have to know that every day. What did I get done today? And then I actually, at the beginning of the week, I write down a list of the stuff I'm trying to get done that week. And then I can see at the end of the week whether I can go back and check it off and see if I got it done. It sounds like I'm way organized, but it's the only way that I keep myself. I don't know whether you noticed, but on that page, there were 4 projects I worked on that one day.
Yeah, same here.
Yeah, I mean, I try to keep that off of my engineers because they need 4 hours of time to work on something, especially if they're doing software. They need a block of time to work on something or they can't get anything done. And so I do more of the interactions that are like several projects a day. That's very typical that I have to do.
Yeah. And I'm the same way. And the funny thing about it is it kind of gets addictive. You kind of get used to this adrenaline rush because you're going from project to project, doing different things. And so I'm not sure if I could go back to the old days where I worked on one problem for 2 days or 3 days straight. I have to have variation. I hope you guys, that's one thing I really hope y'all are getting out of what we're saying. I hope you can tell how much Tommy and I love electronics and love engineering. I mean, I know I wouldn't do anything else but this.
I will tell you, I had a wild hair when I got out of college. I applied to and was accepted at law school. And I went to law school for 2 semesters. And I found out, not because I was doing so badly, but I just found out that it wasn't for me. And I went back and the following year, I went back and got started into a master's in electrical engineering. And I felt like I'd come back home.
Right. Yep.
Definitely.
Well, what questions you guys have? we hate to dominate the whole conversation.
No, we're enjoying your discussion. Do you,
Maybe it's what got them, they say they really like electronics, so like what got them into it in the first place. But
Okay.
that might be a-
Specifically,
Yeah.
okay,
that might
so
be
our in-person student is asking, could you tell us what event or what got you specifically interested in electronics in the first place?
So what happened with me is I was, I grew up in a little town right on Galveston Bay. It's called Bay Cliff. And it was really a backwater. And so you realize I was born in 1950. So there was no NASA, there was no Johnson Space Center, there was nothing. So all there was over there was a 2-lane road that is NASA Road 1 now. That was a 2-lane road. It was what we refer to as a pea gravel road. And we used to drive along that road. There wasn't anything but cow pastures on either side. So you have to realize that all of a sudden we had this space program come and fall right in our laps. That's about 10 miles from where I grew up is where Johnson Space Center is. So I started seeing all that. It was just fascinating to see all the things they were doing, and it developed an interest in that. And quite frankly, I was always very good in math and science in school. That came very easily to me. So from that and just watching that, I just liked the thought of computers and working in that area. And so that's kind of what all attracted me. Of course, I hired people to take it away from. I used to do a lot of software and write microcontroller firmware. I used to do all that a lot and designed a lot of products using that. And then I started hiring people and they were better at it in my view anyway. And I still did all the hardware. So that's what attracted me, was just seeing the fun things, the interesting things they got to do, the technology and that took us to the moon.
I think that's similar to what I ran into in when I was like in junior high and high school. Electronics was really it was a new thing. The transistor was being invented, and we were going from vacuum tubes to transistors, and the space program was was exciting. So it was like electronics was exciting and exotic and kind of cool. and so I really think that was part of it, a lot of it for me also. And then as I got into it, I realized how intellectually challenging it is. And that's one of the things that I've really enjoyed about it is you can stay busy studying electronics and get into as much detail as you want to in a wide spectrum of different areas, all the way from artificial intelligence to RF design or radio design to measurement technology. This field is so large. So I knew
you get to work on everything. I mean, it's just
Right.
amazing the different applications that you work on. And so I've been fortunate in that. So what I really, at some point, probably my junior year, probably I decided I really wanted to do medical electronics, and it was a little hard to get started in that. Find a company in Houston that did that. There were a few, but it was hard to find them, and they weren't really interviewing at that point. And I had been a co-op student at Johnson Space Center, as a matter of fact. I was working there. And then a job opening came at Baylor College of Medicine. I went to work there. I was working on the designing controls for artificial hearts. When I got out of school, that's what I started doing. And so I got immersed in all of that medical terminology, physiology, anatomy. And so I got a really good understanding. I worked there 5 years. And then when I came out of that, I started working for companies because I wanted to design commercial products and not just do research. That was more my interest. And so that's part of the other aspect of that attraction. And I get to work on just the most amazing set of things and the way, what these things do, from, treating cancer to infusing fluids to people who seriously need them, to just a wide range. And developing and understanding enough for you to be able to design those products, you get to be have quite a bit of expertise in a lot of areas. And when you start out, you don't have any of that. I didn't know anything about dialysis machine or the dialysis process. Now I know a lot about it. I didn't know anything about labor and delivery and monitoring the fetus and the mom during that, but I know all about that now. I know a lot about a whole lot of things that I had to just learn. And it's part of what you're getting in college is a basic set of skills in math and science and problem solving, but it's just a very start of the learning process.
Speaking of that learning, I'm sorry, John.
I was just noticing one of the questions from Isaac Suarez. He's asking, what ways have we optimized our learning as technology changes? You want me to? I can address that if you want. If that's a good question. I saw that in the chat.
Yes. Go ahead, please.
Well, I mean, I think these days there's a lot of ways to do it. I like to read electronics magazines. I like to take things apart and see how they work. I like to talk to people who are like Tommy. I mean, we will meet somewhere and talk about how, what we're doing. So I learn a lot of times by talking to other people who have done something that I haven't done. And, and then I just like looking at electronics or looking at systems and seeing how people are doing stuff. There's just all kinds of different electronics. And that, so there's a lot of different ways. Once you get into it, you'll find that your job will teach you a lot. And if you want to get continuing education, I mean, these days you can take classes from all over the world in any subject you want. And so that's some of the ways I would say we optimize our learning as technology changes.
Gotcha. Thank you. Let's see.
To run through the specifics for the engineering.
Oh, that
For the
was,
degree.
yeah, since we don't have a professor, it shouldn't take more than 10-ish minutes. So, Isaac Suarez says thank you. So yeah, thank you.
Sure.
Are there any more questions about electronics or about anything you may want to ask Mr. Cooper, Mr. Martin? Or I guess I have a question that sort of pertains to this question of the change in technology over time. And have you noticed let me think about my question. Between the skills, hold on. Okay. Between the skill sets you developed in your college days and the skill sets that you're using now, what would you say was the biggest change beyond problem solving? So beyond just what you learned in college, like I know you guys mentioned being able to keep track of your time and write it out, and so you can bill and stuff. But what else? What other changes have you experienced throughout the course of your career? Like be it like with technology or what have you?
I think the biggest changes I've seen have been how much more digital the world has gotten. The world has become very digital, and also I've seen an incredible explosion of information that's available. And so I saw the other day, I saw Bill Gates mention the two things that he thought were the biggest changes in his lifetime. He said number one was the graphical user interface. So what you're doing with a mouse right now on a graphical screen, that Bill Gates said was number one. But the next one he said he thinks is coming is artificial intelligence. He feels like artificial intelligence is going to have the same kind of impact that the mouse and the the graphic screen has, which you guys take for granted now. But there used to be a day when everything you did, you had to type letters and numbers on a line on the screen. and you
Called
couldn't pick,
MS-DOS,
do what?
MS-DOS.
Yeah, MS-DOS and before, and you couldn't pick it, you couldn't point at anything with a cursor, and you couldn't pick up something and drag it anywhere. I mean, there was like, geez, how do we ever get anything done?
That's a good question. Speaking about artificial intelligence, do you guys have any thoughts on them well, on that, and maybe how you guys are using it, if you are using it, or something in that sort? Because I spoke to or I was at a conference with the CEO of this actuarial company, and he was speaking about something he was interested in his employees developing was the ability to work with artificial intelligence, namely ChatGPT, to help their work flow and work process. Do you guys have any thoughts or comments on that?
I've got a project right now we're kind of doing in cooperation with Stanford. There's 3 graduate students at Stanford that are doing a project, and if they're successful, it could really be a big help to people like Tommy and me. What they're trying to do is figure out how to use artificial intelligence to read our typical data sheet, right, for a microcontroller right now, which may be 2,000 pages long. So how do you read a data sheet that's 2,000 pages long and get to and answer a question that an engineer has within seconds without making you read the whole data sheet? And so they've been working on this artificial intelligence engine that they feed the data sheet in with using either a PDF or HTML, and then it compiles this database of knowledge. And then when you ask it questions, well, it, theoretically, it's supposed to be able to give you an intelligent answer that's different from and more intelligent than what you would see right there on the page. So you can ask it sort of higher level questions, and it can put together information from the data sheet and say, okay, here's a higher level answer. That if that worked, that would be a huge time saver.
Gotcha.
So right now, I'm not working on projects that are where they're integrating artificial intelligence in. I suspect I will before too long if I stick around for a while. But, I've seen the effect of it. Some of it might be something like this. So they monitor patients in a hospital. And that information is the basic information. It's, their temperature, their blood pressure, their heart rate, things like that, that's on just a standard monitor and a few things. Well, I saw a presentation where they used artificial intelligence to monitor those things, and it would tell them much earlier than a physician could detect it, that they were about to have an episode of an infection in their blood that was potentially lethal, and they could know it hours earlier so they could start that treatment and at least go down to, even if it was wrong, it was okay because it prompted them to go check and figure that out early. And so there's things like that will come out of this that it just increases those kinds of things that it actually surpasses what a human could do, because it couldn't put that trending together of all those variables to show that this is the predicted outcome. So there's things like that are coming. That they're already here. They're already using those. So
Gotcha. Thanks.
The other thing I've just recently seen, there's a company in Israel right now that has developed a program to do design reviews of circuits. And so you could feed a net list and a bill of materials into this their software, and for $200 or $300, they will run this artificial intelligence engine like Tommy's talking about for medicine, but they do it for electronics. And they go through and find all your, everything that might be wrong with your circuit. So it's the equivalent of a group of engineers sitting around looking at something and saying, what could be wrong with the way this circuit's designed? I think that's got possibilities also.
So I suspect it will, I don't know whether it'll come into play, but I suspect it will, because one of the things that we have to do in the medical world, and it is it's risk management. And we have to go through and determine, just categorize and say, here's the risks and harms associated with this product. And here's the mitigation for that. I suspect that is going to be something that they will put the artificial intelligence, that they will analyze your systems and help you with that. Know where you need redundancies and things like that to prevent breakdowns that can, one of the things that we have to design for is single fault failures. We're part of the basic Bible of medical devices and electronics, is you have to design to be single fault tolerant, is I guess the terminology. And I suspect that they will apply it to that.
When you say single fault tolerant, could you expand on what that means?
So if you are designing a system and you have, so when you look at risks and so forth, you initially look at them unmitigated. And then you look at them again after you put in a mitigation, and you can actually categorize the risk as to how dangerous they are. And then you can look at your mitigation and look how effective it is. And then in the end, you'll know what those risks are. So single fault tolerance might be, you have a system that's pulling blood out of the body and putting it through a process and sending it back. So what if you get air in that blood? Well, you can kill somebody with that. Yeah. So is the single fault the air in the blood, or is the single fault the detector? So where's the single fault? Well, it turns out that it's pretty common to get air in the blood when you pull it out. That can happen. And so what they boiled it down to is the fault was in your sensor. The single fault, the first fault would be with your sensor that's detecting air in the blood. They use an ultrasound sensor to do that. So we had to have a detector that said with that air detector, at the fastest flow that it went from that air detector to the patient, let's say it took 5 seconds or 3 seconds to get there, you had to check that air detector and say, is it still working properly? You had to do a self-test on it. So this is how that occurs. You go through all of those single fault possibilities and design things in to some level to say, if I have a fault, then I have a way of mitigating that so it won't cause a problem. A lot of it has to do with electrical safety. And what if I get a failure, one layer of isolation, and now I have a leakage current that can harm a patient? So you have to have ways of analyzing that. And no, you have to be tolerant to that. So you have to have 2 layers of isolation to protect. Things like that.
Yeah.
Makes sense. Thank you. Let's see. Does anyone in the chat have any questions? Do any of you guys have any questions? Okay. All right. Thank you so much, Mr. Cooper. Thank you so much, Mr. Mart. We really appreciate you coming here, or well, virtually coming here to talk. Yeah,
we appreciate you coming here.
thank you. Thank you so much.
Well, good luck, guys.
Good luck.
If you have questions for us, I'll send it. Your SAC director has my email. Y'all can send me something if you have a question. Let me know.
Yep. It's same here. Good luck. Have fun.
All right. Wait.
Thanks.
Our best with that.
Yeah. So long, guys.
See you.
See you guys. You guys have a good day.
Thanks.
Okay, so hello everyone. I will now briefly go over the requirements within the electronics concentration. I'm not a professor, so I can't give you a full breakdown of all the courses and all the material, but I can give you a brief rundown of what you can expect to see. So as you guys may have heard from yesterday from Dr. Chambetta's talk on what a concentration is, at some point, usually like within your second semester of your junior year, you start taking your concentration electives, or where you pick a concentration and then you take electives based off of that. So within the electronics concentration, these classes in blue are the classes you all will have to take if you are to do this concentration. They are circuits and systems, analog electronics, digital electronics, and physical principles of solid state devices. And then from there, you can pick 3 additional courses from this section that I'm highlighting. And there's a bunch of different things, pretty wide array of courses you can take to expand your electronic skill sets. I know that one pretty popular one among electronics concentration students is CMOS analog integrated circuits. And then of course, all of these are good options for you to learn more about electrical engineering and a bit of electronics as well. Let's see. So yeah, so here are some of the some information on analog electronics, digital electronics. We are no longer offering the instrumentation electronics, so feel free to ignore that. Let's see, so some of the requirements. This is an integrated circuit. Yes, we also have our, you can also choose to take 5346 VLSI design. And then, as I mentioned before, CMOS analog integrated circuits. So essentially, integrated circuits are the form of chips that are most popular nowadays. You'll find hundreds of them in whatever device you want, or even within a car, for instance. Okay, and yeah, that's it for the electronics concentration. Thank you, everyone.